In today's session, I am going to teach you on probability and distribution. So, what is probability? So, probability implies likelihood or chance. So, when an event is certain to happen, then the probability of occurrence of an event is 1. And when it is certain that the event cannot happen, the probability of that event is 0. So, hence, the value of probability ranges from 0 to 1. So the classical definition for a probability is, as the name suggests, the classical approach to defining probability is the oldest approach. It states that if there is there are n existing events, there are n exhaustive, mutually exclusive, and equally likely cases out of which m cases are favorable to the happening of event A. Then the probability of event A is defined by probability of A is number of favorable outcomes of A divided by total number of outcomes. So it is nothing but a probability of something is. So what is the favorable outcomes that for a particular probability is, and then the total number of outcomes. Okay, so if you take a crossing or a coin, so what is the probability of getting head? So if we see when you cross a coin, then there is probability of either head or tail, right? So the sample will be tail, comma, head. So what is the probability of getting head? Is 1 by 2. The sample size is 2, and the probability of head is 1, right? So number of outcomes favorable to head is 1, total number of outcomes is 2, hence the total probability of head is 1 by 2. Probability basic concept. So there is a random experiment. An experiment is said to be random experiment if its outcome can't be predicted with certainty. So if a coin is tossed, we can't say whether head will come or tail will come. So it's a random experiment. Sample space, a set of all possible outcomes of an experiment is called sample space. It is denoted by S and its number of elements are n of S. So let's take an example. If you roll a dice, okay? So what are the possibilities? You can get 1, 2, 3, 4, 5, or 6. Okay, if you roll a dice, there are 6 possibilities. So the sample space is 1 comma 2 comma 3 comma 4 comma 5 comma 6. So what are these are the sample space, and the sample size is n of s, that is 6. That is number of samples is going to be 6. Okay, similarly case of coin, head comma tail with sample space and number of samples is 2. Okay, this is number of samples. Sorry, if I have mentioned before the sample size, that is number of samples. Okay, as I said, so that is number of outcomes. Okay, the probability is number of favorable outcomes to A divided by total number of outcomes. So from this, let's move to the next. So event. So event is every subset of a sample space is an event. Okay, every subset of a sample space is an event. It is denoted by E. So let's consider an example. You're throwing a dice. What is the possibility of an even number will occur? Okay, so the event will be 2 comma 4 comma 6, and this event will always be subset of a sample space. Okay, so you can see event E246 is subset of sample S. So now let's move to the next concept. So equally likely events. Events are said to be equally likely if the probability of occurrence of the events are same. Example, when a dice is thrown, all 6 faces has equal likely outcome. Okay? And what is exhaustive events? When every possible outcome of an experiment is considered, then that is an exhaustive event. Okay, the a dice is thrown, cases 1, 2, 3, 4, 5, and 6 form an exhaustive set of events. So now let's come to mutually exclusive or disjoint event. Okay, so if two or more events can't occur simultaneously, that is, no two of them can occur together. Okay, so let's consider when you toss a coin, the the event of occurrence of head and the event of occurrence of tail are mutually exclusive. I mean, so if you toss a coin, there is no possibility that head and tail occurs at the same time. They are either head will occur or tail will occur. So it is not possible that head and tail occur at that time. So that is known as mutually exclusive events or disjoint events. So if I can give example, if you are going in a straight road and you have to take a cross, there is either left or right you can take a cross. You can't go, you can't take two crosses at the same time. You can't go left and right at the same time. So that is known as mutually exclusive event. And you have to note that I will let me explain about independent. So independent or mutually independent events. Two or more events are said to be independent if occurrence or non-occurrence of any of them does not affect the probability of occurrence or non-occurrence of the other event. So let me take an example. When a coin is tossed, the event of occurrence of head in the first throw and the event of occurrence of head in the second throw are independent events. Like let's say when you toss a coin, you get head. When you toss again, the first whatever result you got for the first time, it is not going to affect or influence the result of the second. Okay, so if you get first when you flip a coin, if you get an head, and in the second trial also you can get if you get an head, the first didn't influence for the second trial. Okay, you have to consider that. So, what does it say? Two or more events are said to be independent if occurrence or non-occurrence of any one of them does not affect the probability of occurrence or non-occurrence of the other event. Okay, so the first event which we did is not going to affect the second event that we did. What is the difference between the mutually exclusive and mutually independent events? Okay, mutually exclusive is used when the events are taken from the same experiment, whereas independence is used when the events are taken from different experiments. Like as I said, you're going to toss a coin. It's not possible that you will get head and tail in that same experiment. But if you toss a coin twice, there is a chance that in the first attempt you may not be able to get head, but in the second attempt you may be able to get head. Okay. So does it say? So in the first experiment, it's it's unlikely that you get head and tail both at a time in the first time only. But in the second experiment which we perform, may be a possibility that if the first attempt is in the first attempt, if we get head, then in the second attempt we might get tail or head also. So you have to understand mutually exclusive takes consider into the one event and mutually independent events takes consideration of two events that's going to happen which are independent of each other. So let's come to additive theorem of probability. So for non-mutually exclusive events, you have to understand this additive theorem of probability is only for non-mutually exclusive events. In that case, what will happen? I'm going to read the statement. So if A and B are not mutually exclusive events, if A and B are non-mutually exclusive events, the probability of occurrence of either A or B or both is equal to probability of event A occurs plus the probability of that event B occurs and minus the probability of occurrence of events common to both A and B. So let's say you are picking, let's say you are actually let me consider an experiment where you are going to pick a ball from a ball and also you're going to pick a card from a deck. Okay. You're going to pick a ball from a box which contains four colors. Okay. And you're going to pick a card from a deck which contains 52 cards. Okay. So what does it say? If A and B are not mutually exclusive, the probability of occurrence of either A or B or both is equal to probability that event A occurs plus the probability that event B occurs minus the probability of event occurrence of events common to both A and B. So I will give the examples in the later section as we pass because I have already included one example, task also. So let's see in that. So just understand this. definition, okay, for now. So P of A union B is equal to P of A plus P of B minus P of A intersection B. So P of probability of that A occurs plus probability of B occurs minus probability of A and B both occurs at the same time. So if both occurs at the same time, then we have to subtract one time, right? So since we are adding twice here, here also we are adding that event, here also we are adding. So we are subtracting the intersection point where both occur simultaneously. So for mutually exclusive events, the probability is if A and B are two mutually exclusive events, then the probability of occurrence of either A or B is the sum of individual probabilities of A and B. This is because in mutually exclusive event, there is no way that it's going to like intersect. There is no intersection. That is P of A intersection B is zero. It is impossible. As I said, mutually exclusive is an event which we are taking concept of only one experiment. So this is impossible that they can be an intersection. Okay. So let me take an example over here. So additive theorem of probability examples. So for non-mutual exclusive, this is for non-mutual. So a shooter is known to hit a target 3 out of 7 shots, whereas another shooter is known to hit the target 2 out of 5 shots. You find the probability of the target being hit at all when both of them try. So what they are asking is, so P of A and union B, okay? Probability of shooter A hits the target and shooter B hits the target, but how many times they are asking the probability that both shooter hits the target. I mean, it's not like they're taking intersection. It's like what are the possibilities that either shooter A hits the target or shooter B hits the target. Okay. So total probability they are asking. So probability of A union B we have to consider where A is also, where we have to find out probability of A. That is probability of A shooter A is 3/7, whereas another shooter probability of B is 2/5 minus probability if both shooter hits the target. We have added the 3/7 and 2/5 already. So if both shooter hits, then 3/7 into 2/5 we have to subtract. So let me take this the solution. Probability of first shooter is 3/7. Probability of second shooter hitting the target is 2/5. Even A and B are non mutually exclusive. Okay, these are mutually these are mutually not mutually exclusive as both the shooters may hit the target. Hence, the additive rule says that P of A union B is 3/7 plus 2. 3/7 comes out to be 23 times out of 35 times. The target will be hit. Okay. Solution 2. So I would like you to solve the second example by your own. Just think how you can solve this. And I'm going with the next example part. Similarly, here also I want you to solve the second one. So first one I will take. A card is drawn from a pack of 52. What is the probability that it is a king or a queen? So they are saying probability of king or queen. Okay. So in a deck of 52 cards, how many king we have? 4, right? And how many queen we have? 4. So what is the probability? This is mutually exclusive, okay? So the probability of king or queen is probability of king plus probability of queen. That comes out to be probability of king 4/52 plus 4/52 for probability of queen, which comes out to be 8/52 or 2/13. So next, now let's come to multiplicative theorem of probability. So for independent events, that statement says, the theorem states that the probability of the simultaneously occurrence of two events that are independent is given by the product and the improbability probabilities. That is, P of A and B is P of A into P of A. This is for independent events. What are the intersection? Okay, the theorem states the probability of simultaneous occurrence of two events are independent that are independent is given by product of individual probabilities. And for dependent events, the conditional probability comes into picture. If we recall dependent event, so let's say you are picking a ball from a where there are if you are there are 20 balls in a box and you are picking one ball which is red color, and there are some there are different colors in the box. So what is the probability that there are 20, let's consider there are what is the probability that the second ball is going to be red color, okay? So if we say there are 20 chances of we getting, there are total is 20, right? So in the first attempt when you grab a ball, there is a 1 by 20th times you are going to get. And in the if there is only 100 ball, right? But if you are making taking the ball after without displacing, let's take an example of something else, okay? Yeah, I will give you an example in the assignment problem that we have. So just understand probability of event B, this is read as probability of event B given A has already occurred is probability of A intersection B, that is probability of A for independent events divided by probability of A. So if we, that I will read the definition now. If we recall dependent event, the earlier stated multiplicator theorem is not applicable for independent dependent events. For dependent events, we have another theorem called conditional probability, which is given the probability of event B given event A equals probability of event A and event B divided by probability of event B. I will give you an example with this. Let me move to the next slide. So multiplicative theorem, conditional probability examples. Okay. Independent events. You have a cowboy hat, a top hat, and an Indonesian hat called songkok. Okay. You also have four shirts: white, black, green, and pink. If you choose one hat and one shirt at random, what is the probability that you chose black and black shirt? So this is in for independent events. Okay. So for independent event, probability of A intersection B is probability A and B is probability of A into probability B. They are asking if you choose one hat and one shirt at random, what is the probability that you choose the strong cock and black shirt? Okay? So let me see the probability of getting the song cock. That is, we have four hats, one, two, and an Indonesian hat and a sangkok. Sorry, there are three possibilities, right? A cowboy hat, top hat, and an Indonesian hat, sangkok. Okay. Probability of we getting sangkok is 1/3, and we have four shirts. Probability of we getting black shirt is 1/4. The probability of we getting black hat and songkok is probability of songkok into probability of black shirt. So that is going to be 1/3 into 1/4, which is equal to 1/12. Okay, 1/12 probability of this probability of that which you songkok and black shirt is 1/4 into 1/3 equals 1/12. So let's move to the multiplicative theorem of conditional probability examples. So this is the answer that is already given. So here you can check the probability of choosing Sankok 1/3, probability of choosing black shirt is 1/4, and multiplication theorem, probability of both is 1/12. So dependent event, right? So an urn contains 20 red balls and 10 blue balls. Okay. Two balls are drawn from bag, one after the other without replacement. What is the probability that both the balls are red? So let's take the first event that we are performing. Two balls are drawn from a bag, one after the other. So first I'm going to take one ball, and that is without replacement, right? So and contains 20 red balls and 10 blue balls. So what is the probability of me getting probability of me picking a ball which is right? What is the probability that both balls are red? Probability of me getting the first ball as red is 20/30. Okay. And in the second experiment, we will have only 29 balls. Okay. Because I have already taken one red ball. So they are asking what is the probability that both balls are red. So in the first experiment, you already have one red ball. What is the probability of second experiment? Is also red. So now it is going to be 29 total probabilities. So 19 by 29. So in first is 20 by 30, and in second is 19 by 29. Since we have only 19 possibilities, since we had already taken one red ball out of that total balls of 30. So as I say, so it's going to be, as I said, let A and B denote the events. First and second ball down red balls. We have find A intersection B or A and B. Probability of red balls in first round, as I said, 20 by 30. Now only 19 balls and 19 red balls and 10 blue balls are left in the bag. Okay. Probability of drawing a red ball in the second draw. 2 is an example of conditional probability where drawing of second ball depends on drawing of first ball. Okay. Hence, conditional probability of B on E will be probability of E given A has already occurred is 19 by 29. By multiplicative theorem, probability of E and B is 19 by 29 into 20 by 30, which is equal to 38 by 87. So that is that there are 38 chances of we getting both red balls out of 87 pickings. For detailed discussion of multiplicative rule probability, download by okay. So that's it. So now let's come to Bayes theorem. This is an important concept, one of the important concepts that you must know. So Bayes theorem is named after Thomas Bayes. Bayes theorem describes the probability of event based on prior knowledge of conditions that might be related to an event. Note, the conditional probability is known as hypothesis. This hypothesis is calculated through previous evidence or knowledge. The conditional probability is the probability of the occurrence of an event given that some other event has already happened. The probability of given event B is already occurred, you have to read like this. Okay, probability of event A given B is already occurred is equal to probability of event B given A is already occurred into probability of A given probability of A. So I will give you an example here. Suppose the weather of the day is cloudy. Understand? Suppose the weather of the day is cloudy. Now we need to know whether it would rain today. Okay, given the cloudiness of the day. Okay, so therefore you are supposed to calculate the probability of rainfall given the evidence of cloudiness. Okay. I will read again. The weather is cloudy. Now we need to know whether it will rain today given cloudiness of the day. Therefore, you are supposed to calculate probability of rainfall given the evidence of cloudiness. So we know from Bayes theorem that P of A given B is probability of A intersection B by probability of B. This is for conditional probability. And similarly, probability of B given is also probability of B intersection by probability of A. So if we rearrange this thing, probability of A intersection B is equal to probability of A given event B is already occurred into probability of B. And similarly, probability of B intersection is A is equal to probability of given B given A already occurred into probability of A. Since we know one thing that probability of A intersection B is equal to probability of B intersection A always. So we are equating this equation with this equation. Okay. Then we get probability of B given A into probability of A is equal to probability of A given B into probability of A. So this is how we were able to get that probability of A given event B is already occurred is equal to probability of B given A already occurred into probability of A by probability of B. Okay. So let's come to Bayes theorem generalized form. So before going with the generalized form, I wanted to teach some other concepts as well. So this is for Bayes theorem. Let's say you have to filter out some spam emails. Okay. So what you will do first, you will take emails as spam. We have to probability of what we have to find probability of emails of spam given that content of the mail. So what you might have done before is you might have filtered out the email first based on the content. So P of E2 by E1, like probability of content of the mail given email as spam. Okay. So content of the mail would be dollars, lottery, one, free. Those kind of emails are termed to be spam. Okay, so you already had an what is the probability of content of the mail given the email as spam. So now you want to calculate probability of spam given the content of the mail. You have the emails and you have to now predict if it's a spam or not based on the previous findings. Okay, this prior probability is P of E2 by E1. That is prior probability is on before that is already occurred, and we are now finding probability of E1 given E2, probability of spam given content of the mail. And this can be calculated by probability of spam intersection content of the mail divided by probability of content of the mail. So let's see, using multiplicative theorem, we have already seen the formula over here. Probability of A given B is probability of B given A into probability of A by probability of B. So now let's come to the generalized form of Bayes theorem, and this is very, very important, okay, to understand, okay, probability of, see, when an event generalized, so forget about this, and just focus on this. So probability of event head given event, probability of head H given event E is already occurred is equal to probability of E given H has already occurred into probability of H divided by probability of, this is the formula we have for now. Okay. Now let's consider, you know that probability of E by H, this, you know that this is a prior probability. As I said before, this is a prior probability. Okay. So we know that this prior probability, when you consider, you know that for event H is the first event that has occurred. Okay. For prior probability, this event H has already first occurred. So, okay. When H is occurred in an event, it is obvious that H dash also occurs. Okay. When H is occurred, there is a obvious reasons H dash will also occur. So when event H is occurred, then we have seen that event E is occurring. Okay. After when H has occurred, then we are seeing E is occurred. If E is occurred for H, then obviously E dash will also occur. And similarly, if for H dash E will occur, event E will occur, then E dash will also occur. So now, if you want to find out probability of E, so for this, okay, for H E dash and all. So you know, for this, we had first we got probability of H because before H there was not any other event occurred. Okay. And for event E, this thing, we know that probability event E occurred only after H has occurred. So probability of H into probability of E given H. Probability of H is due to this thing because no other event occurred before H, and probability of E given H is event E occurred only after event H has occurred. That's why, okay. So similarly, probability of event H occurred here first, and then only probability if E dash occurred, given H has already occurred. Okay. Similarly, for H dash also you have to do probability of H dash happened, then probability of E happened, given H dash has already happened, and similarly probability of H dash into probability of E dash given H dash. So now we have to find probability of E, okay? Probability of E we want to find because this is not going to be a problem. We can easily identify. Now for probability of E, if you see here, what is the probability of E? E occurs over here in the shaded region in yellow, and E also occurs over here. So probability of E is equal to P of H, P of E given H plus P of H dash into P of E given H dash. Okay. So this is the probability of event E is going to occur. So that is what I was going to explain over here. Generalized form is P of H given E is P of E given H into P of H divided by P of E given H into P of H plus P of E given not H into P of not H. Okay. Just remember like this. Okay. P of this numerator will come here also once again. In the denominator, numerator will come plus the h dash will come. Instead of h, we will have h dash. Whatever numerator denominator value you have given h, so we will get into plus p of h dash into p of e given h dash for the event. So let's say given a transaction, tell me whether it is fraudulent or not. How we can write? So we can write this as probability of what we have to find whether it is fraudulent or not. So it will come fraudulent given the transaction. So now let's go to this. So there is an example for Bayes' theorem, and epidemiologists claim that the probability of breast cancer among Caucasian women in their mid-50s is 0.005. Understand? Breast cancer possibility of having breast cancer is 0.005. So this is going to be our H. What is our H dash then? Not having breast cancer. That is 0.995. Okay. 1 minus 0.005, which comes out to be 0.995. So an established test identify people who have breast cancer and those who are healthy. Okay. A new mammography test in clinical trials has probability of 0.85 for detecting cancer correctly. So detecting cancer means detecting positive. So probability of test positive for cancer is 0.85. So okay, probability of test positive for a cancer is 0.85. So what is the probability of test negative for a cancer? That is going to be 1 minus 0.85, which is going to be 0.1915. In women without breast cancer, now let's come to the H dash part. It has a chance of 0.925 for negative result. Probability of negative by not having cancer is 0.925. Then what is the probability of positive for not having cancer is 1 minus 0.925, which comes out to be 0.075. If a 55-year-old Caucasian woman tests positive for breast cancer, okay, we have, if it is test positive, what is the probability that she is in fact has a breast cancer? You have to find out from this data what is the probability of having breast cancer given that she has tested positive. Okay, probability of cancer given she is tested positive, that is you have to find out. We have the data over here. Yes, actually apply in this form accordingly and you will get answer. Okay, just apply the values for probability of cancer given. I will just explain how. So we have to find out probability of cancer given it is test positive is equal to probability of test positive given cancer into probability of cancer test positive into by cancer into probability of cancer divided by probability of test positive can cancer into probability of having cancer by plus probability of test probability of not what it comes test positive whole dash, right? That is probability of not H, probability of E not H divided to probability of H. That comes out to be like P of H dash, right? P of H dash. H is H dash, okay. Probability of, as I said, probability of H. That is 0.005, okay. Then plus, I would like you to solve this on your own, but it's just you have to substitute in this formula that I have given. P of E given not H is put 10 to the power of not H. So probability of test positive given cancer is the probability of having cancer, that is 0.85 into 0.05 divided by probability of test positive into cancer, once again 0.85 into 0.05. Probability of test positive given not cancer, probability of not cancer, that is 0.075 into probability of not cancer. That is 0.995, having not breast cancer. Okay, you multiply on that and substitute, you will get the answer. Okay. Mm. The semantic works by having user train the system. It looks the pattern in the words in emails marked as spam by user. For example, it may be learned that for the word free appears in 20% of emails marked as spam. So probability of free by spam is 20%, that is 0.2. Let's see, probability of free given spam is 0.2. Assuming 0.1% of non-spam mail include the word free. Probability of free given non-spam is 0.1%, 0.1%, that is 0.001. And the word and 50% of all emails reduced by user is spam. Probability of spam is 0.5. Find the probability that the mail is spam if the word free comes into question. Probability of spam given free. We have to find out. So just substitute in the previous formula that we have discussed. That is going to be probability of spam given free is probability of spam 0.5 into probability of free given spam 0.2. Probability of divided by probability of spam into probability of free given spam. That is once again 0.5 into 0.2 plus probability of not spam into probability of free given not spam. Probability of not spam is 0.5, right? 0.5 into probability of free given not spam, that is 0.001, which comes out to be 0.995. So now we have finished this base theorem. Now we are going to teach random variable. I'm going to teach you about random variables, that is discrete and continuous. So random variable, so a variable that can take multiple values with different probabilities. So if you see the points scored per game, in the 0th game, they have scored 1 point. In the first game, they have scored 4 points. In the second game, they have scored 6 points. In third game, they have scored 12 points. And similarly for fourth, fifth, and sixth game. So mathematical function describing these possible values along with their associated probability is called probability distribution. See the frequency if you want to find the probability, the frequency we have. So if you want to find the probability of this 0th game scoring in the 0th game, that's 1 by total number of games, that is 30. Total number of goals, I guess 12, 5, 17, 18, 19, 25. Total number of points scored, that is 30. So it is 1 by 30 is the probability of scoring point in the first game. 4 by 30 is the probability of points scoring in the second first 0th game is 1 by 30 probability. And in the first one point scored per game is 4 by 30, and similarly second is 6 by 30. Similarly for others. Okay. So this leads to descriptive statistics, this leads to inferential statistics. Maybe I don't know. Then let's come to the random variable types. Before coming to random variable types, I would like to teach you about this probability distribution function. As I said, there are two types in random variables, discrete and continuous. In discrete, let me take an example of causing 2 points together. So what is the probability of getting heads? What is the probability of getting to one head? What is the probability of getting no heads? And what is the probability of getting two heads? So probability of getting 0 heads is 1 by 4 because we can get both tail. Probability of we getting one head is 1 by 2 because 2 by 4 divided is equal to 1 by 2. And probability of we getting two heads is 1 by 4. So this is the probability function that we have done. Probability of 0 is 1 by 4. Probability of 1 is 1 by 2. Probability of two heads is 1 by 4. So according to probability mass function at 0, we have 1 by 4. Probability mass function at 1 is 1 by 2. Probability of mass function at 2 is 1 by 4. And probability mass function at 3 is 0. This is all about probability mass function. Okay. Now let's come to continuous. So in continuous, if you have seen that in H.C. Verma textbook volume chapter 1, in your 11th standard, there was a concept related to integration. Okay, so if you want to find the area under this curve from x to x plus delta x, then you have to integrate over x to x plus delta x and the area and the function of this curve. Okay? So area under this curve is integration goes from a to b and given the function of this curve. Now let's find out the probability density function is this. So probability, let's find out the cumulative distribution function. So for a cumulative distribution function, it goes from minus infinity till x. So let's consider this as a instead. So cumulative distribution function is minus infinity to a, and the probability density function we have to pass. That is going to be a cumulative distribution function. And sorry, I didn't tell you about the cumulative distribution function for this. When you want to find out cumulative distribution function at 2, you have to find out cumulative distribution till 2. That is probability mass function of 0, probability of mass function of 1 plus probability mass function of 2. That is going to be total is equal to 1. And if you go to calculate a cumulative distribution of function at 1, you will have probability mass function at 0, probability mass function of 1. That is going to be 1 by 4 plus 1 by 2. That is going to be 2 by 3 by 4. Okay. Now let's come back to the continuous distribution function. Cumulative distribution function for a continuous variable. This goes from minus infinity to a into probability density function. This is, that this is the area under the curve. Okay. This division is the area under the curve. So this cumulative distribution function for a discrete variable is this from minus infinity to x probability mass function, whereas cumulative distribution for a continuous variable is cumulative distribution function for continuous minus infinity to a into probability density function. Okay, this is the probability density function that I was talking about. Now let's come back to this concept of discrete and continuous. This is discrete is countable, whereas continuous is measurable. Okay, it's not countable, it's measurable, continuous. Let's do some comparison. Okay, so probability mass function, probability density function, discrete distribution. So in a discrete distribution, probability that x can take a specific value x is p of x. Probability that x is between 2 points a and b is p of x greater than a less than b, and probability of integral a goes to be f of x dx. It is non-negative for all real x, and this is also non-negative for all real. The sum of probability all p of x or all possible values of x is 1. It always take into consideration for this. Sum of probabilities has to be 1. And similarly, integral minus infinity till infinity f of x dx is equal to for a continuous distribution. Here we will find continuous probability mass function. Here we will find the probability density function. So now let's come to the concept called discrete distribution of binomial, that is a binomial distribution. So in a binomial distribution, a distribution where only two outcomes are possible. Okay, binomial means 0 or 1, okay, or true or false, or win or fail. Okay, such is binomial. That's why such as success or failure, gain or loss, win or loss, and where the probability of success and failure is same for all the trials is called binomial distribution. The outcome need not be equally likely. Okay, each trial is independent in binomial distribution. Here you have to understand that binomial distribution is a discrete distribution and each trial is independent. The outcomes need not be likely naturally, and a total number of n identical trials are conducted. The probability of success and failure is same for all trials, and mathematical representation is this. Probability of x is n factorial, that is, this starts the count of number of ways even can occur. Okay? And divided by n minus x factorial, this ends the count of number of ways event can occur. This is obviously n. The x is this deletes the duplication, and p of x is the probability of success of x trails, and p of x is probability of failure for x trails. Okay, this is the binomial distribution for a sample where n is number of samples is 20 and probability is 0.25. Okay. Now let's come to continuous distribution. This is very important. You have to learn this concept. In continuous distribution, we have normal distribution. So normal distribution represents the behavior of most of the situation in the universe. That is why it's called normal distribution. The large sum of random variables offers turns out to be normal distributed, contributing to its widespread application. So, well, let's see the characteristics for a normal distribution. So the mean, median, and mode of the distribution coincide, but mode can or cannot be, but mean and median will always coincide for the normal distribution. The curve of the distribution is bell-shaped and symmetrical about the line x is equal to mu, and the total area under the curve is always 1, and exactly half of the values are to the left of the center and the other half to the right of center. Here the center is the mean or median since it's to the same value. So center is the mean. A normal distribution is highly different from binomial distribution. You have to understand that normal distribution is continuous is variables, and binomial distribution is for discrete distribution variables. So a normal distribution highly different from binomial distribution. However, if the number of trials approaches infinity, then the shapes are quite similar. You can see the shapes are quite similar if there are infinite number of samples, infinite number of trials, that is trials. Okay, and now let's come to the normal distribution. Another thing in normal distribution, we have central limit theorem. Okay, the central limit theorem in statistics states that given a sufficiently large sample size, the sampling distribution of the mean for variable will approximate the normal distribution, regardless of that variable's distribution in the population. So it's like you take a population data set and take samples from that population data set. And for that samples that you have taken, calculate mean and standard deviation. When you draw a normal distribution curve for that, whatever values, whatever mean and standard deviation that you have calculated, now whatever mean you have, now if you whatever mean you have that for the samples, if you plot a node, if you actually plot that curve, then it will follow a normal distribution, you know. So in layman's term, even if the data is not normally distributed, the mean of the distribution are normal distribution. So this is like the mean of whatever samples that you have taken, that follows normal distribution. Okay, provided the sample size is large. Why is it useful? We can use means normal distribution, okay, to make confidence intervals, performance hypothesis testing. So now let's come to normal distribution central limit takeaways. So these are the key takeaways. So the central limit theorem states that the distribution of sample means approximates a normal distribution as the sample size gets larger. Sample sizes greater than 30 are considered sufficient for central limit theorem to hold. The key aspect of central limit theorem is that average of the sample means and the standard deviation will equal to the population mean and standard deviation. Okay, the average of sample means on standard deviation of samples is equal to the population mean and standard deviation. A sufficiently large sample size can predict the characteristics of a population. Okay, so the expectation of sample mean as a random variable is population mean. Symbolically, E of x bar should be mu. Standard deviation is sigma by root n, where sigma is standard deviation of the sample and n is the sample size. Okay. So normal distribution empirical formula, empirical rule. You have to know this. The empirical rule states that for a normal distribution, nearly all of the data points will fall within three standard deviation of the mean. That is three standard deviation of the mean. You have to understand the empirical rule can be broken down into three parts. Okay, so 68% of data falls within the first standard deviation from the mean. So here is the mean. Okay, this is the mean, and 68% of the data falls within the first standard deviation from the mean. That is from both hand sides. Okay, mu minus sigma to mu plus sigma, where mu is mean and sigma is the standard deviation. 95% of the fall within two standard deviation. That is mu minus 2 sigma to mu plus 2 sigma. 95.54% of the 95.45% of the data points fall in this standard deviation, and 99.7% fall within three standard deviation. This is always hold true. The 99% of the fall within three standard deviation given the curve is a normal distribution curve. Okay, so you have to remember the 65, 99, and 99, 95, and 99 7 rule. So PDF, that is probability density function of a normal distribution and origin of empirical formulas. Function PBDF function is given by 1 by sigma into root pi root 2 pi into e power minus 1 by 2 x minus mu by sigma. So for a normal distribution with mu is equal to 0 and sigma is equal to 1, standard deviation we will get in this form. Okay, let me show you. So this is the empirical rule, minus sigma to mu plus sigma 60.22, until two standard deviation we have 95.45, and with three standard deviation we have 99.73% of the data points lying. So what's the cumulative distribution for? Let's calculate the cumulative distribution from mu minus sigma to mu plus sigma. Okay. So that will goes from mu minus sigma to mu plus sigma. Let's say mean is 0 and standard deviation is 1. It goes from minus 1 to 1. The probability density function for a normal distribution is this. Since we have given mu as 0 and sigma as 1, just apply this in the formula that we have given. So that is standard normal distribution. Okay. So we are converting the normal distribution into standard normal distribution. So you have to understand when you are converting normal distribution into standard normal distribution, then mu becomes 0 and sigma becomes 1. When you apply this will be the formula that will be the end answer 1 by root 2 pi into e power minus x square by 2. Okay. So empirical formula of a normal distribution. Okay, the empirical rules also referred to as 3 sigma rule. I have already told. It's a statistical rule. It states that for a normal distribution, almost all data fall within three standard deviation of the mean. As I said, broken down the empirical rule shows that 68% is first standard deviation, almost 95% within the second standard deviation, first two standard deviation, and almost 99% of the first three standard deviation. Okay. So if you just apply the values over here, you will get an answer. And let's see the normal distribution origin of z-score. Okay. So we have been discussing z-score. Let's see the normal origin of z-score. So z-score gives how many standard deviation away from a mean a value is. So, however, to understand the probability associated with it, we need to refer to the z-table. Okay. So let's solve some question. Comparison of two different normally distributed values, then z-score is enough. Finding the probability or percentage of values, then also we need z-table. Okay. So let's see. Happy and Ekta are two students. Happy scored 65 marks in math exam, while Ekta scored 80 in English exam. Given that both math and English marks follows an approximate normal distribution, who perform better? So see, we have two students, Ekta and Happy. So Happy scored 65 in English, whereas Ekta scored 80 in. So Happy scored 65 in maths, whereas Ekta scored 80 in English. If you see this, you might say that Ekta has performed better, but no, that's not the case. You have to consider here the class mean and as well the standard deviation. Okay. So based on the Z score, we will be able to tell how much percent, by how much percent Ekta or Happy has performed well over other students in their class. Okay. So if you see in this example, so let's first convert the Happy. Let's standardize first. So standardize for calculate the Z score first. Z score is x minus mu by sigma. X is 65 for Sharma ji Happy, and 65 minus mu is 60 by sigma is 4, and Z for Happy is 1.25, and Z for Ekta it's x minus mu. X is 80 minus 79 divided by 2. Z for Ekta is zero point 0.5. So if you see when we draw Z table, when we draw the normal distribution and draw it and make sure that let's see we have a mean of 0. Since we have performed standard normal distribution, we have mean 0. So now we have a z score of 0, z score of 0 0.5, okay, and z score of 0.125. For these values of zero point 0.5 and 0.25, we will see, we have to see how much of the percent of the, how by how many percent of students she has done well. Okay, so if you see Ekta compared to Ekta, Happy has performed better, because even though if you see the marks is less, have Happy compared to Ekta, but if you see the mean of the class here, it is 60 and mean is almost 79. Okay, and standard deviation is 2 here and standard deviation is 4. But when we have performed the standard normal distribution and when we had standardized, you can see the z score of Happy comes out to be 1.25, whereas Ekta comes out to be 0.5. If you see this region from here to here, so whatever values come less than zero point 0.5, so these many students have performed not much, not better than Ekta, but yes, more than, you can see this percentage of people have performed better than Ekta, but only this much percentage of people have performed better than Happy. Okay, so we can say that if you see the Z table, so let's check Z table and let's find out the answer from it. So, so okay. Mm, okay, we have image. Let's see that. Okay, so if you see this table, Z table, it gives the probability. Okay, so for our example that we have taken, Happy Z score is 1.25, and whatever you will get the percentage value, it is this region. Okay, this region is the percent. So let's see the for Z score of 1.25. What's the percentage of? What's the percentage? So 1.25. So one is over here, and we have to say 0.25. So 0.2, 0.2, 0.2, 1.2. Let's see 1.2 here and 1.205, 0.05, 0.05 over here. Okay. See, if you see this, you can see Happy has performed better than 89.44% of the students in their class, and only 1 minus 89, 100 minus 89.44, that is almost, I would say, 10.56% of the students have performed better than Happy in their class. Whereas if you consider the same example for Ikta, where z score is zero point 0.5, let's see the z score of zero point 0.5, we have 69.15% of the people are not she has performed better than 69.15% of the people. But if you see how many percent of the people have done it better than Ekta, then you see 100 minus 69, it comes out to be 30 point, sorry, 30.85% of the students have done better than Ekta. So you can see 30.85 and 11 points. So there is high percentage of students that have done not that has high percent of students that have done very less compared to happy. But if you, so according to Z score, you can say the performance of happy is much better compared to performance of A. So this is the area under of area happy score is minus infinity till 1.25. This comes out to be probability density function. It comes out to be people who perform better than happy is 1 minus area under curve, this thing. So this is all about the probability and distribution that I wanted to discuss. And in the coming sections, I'm going to teach you about hypothesis testing. Thank you.